Hello, welcome to the model question paper of ESM course, Embedded Systems and Microcontroller. What I plan to do is I will record the part A questions first and then the part B questions. Later on, I will give you a summary of all the ARM Cortex M0 instructions, okay, for a reference. So let us start now, and this is going to be for 30 marks, and the duration is 2 hours. Whatever questions you see here, and then I will also be explaining something around it, and you can expect that the actual question will have from any of those topics that I am covering here. Okay. Now let us look at the first question. What is an assembler tool and when is it used? And what is the input and output of a RP2040 assembler? Now you may wonder that for 1 marks I am asking too many questions, but it's to give you a good overview of what is required to be covered and what you should know. Okay. So let us just talk about tools now. What are the tools that we have learned in the course? Compiler, then assembler, linker, and loader. Now what is the sequence? Let me call this as C, A, L, and maybe loader. Okay. Now what is the input? It could be a C program or a C++ program, right? Any of this. No, I am not bringing Java or Python here. Okay, let us stop with this two languages. The reason is that it is going to generate a code which is specific to a processor and not a byte code like what happens with Java and Python. So this is the compiler. First compiler is the tool. Input is a source file and it also includes header file. Then it tries to understand the syntax, whether you are following the syntax, and then the semantics in terms of whether you are using the data types properly, assignment is done, and are you calling the library function properly based on the link include files that you have given. It checks everything, and then everything looks fine, then it generates a obj file. Now what is obj file? It's an object file. Now what does it contain? The obj file is a binary file. Why do we call binary file? Because if you open it in a text file or a Word document or whatever, even a Word document is a binary file because you can't understand it by opening it in a text editor like Notepad or a WordPad. Now even this obj file, if you open it in a WordPad or a Notepad, you won't be able to understand because it's not a ASCII characters, it's a binary information which is encoded into the file. Now what does it contain? Since a compiler is always meant for converting a high level language into some assembly languages, okay, it could be based on what processor you are compiling the source code for. Now in our case we are interested in compiling it for RP2040, which internally has ARM Cortex M0 plus processor in it. Okay, please remember ARM also has many flavors and the instructions differ one from the other. So we need to know in RP2040 what is the particular ARM core which is running, actual ARM processor which is inside, and then the compiler we should choose such that it generates the assembly instructions which is understandable by the Cortex M0 plus core. Now what does the obj file contain? It contains the binary form of assembly instructions. Now what I mean by binary form of assembly instruction? Suppose you are all aware of one instruction called R0, R1. We are moving the content of R1 into R0. Now this needs to be encoded in the instruction. Okay, as I told you, many of the instructions in ARM Cortex M0 Plus are thumb instructions. Okay, now what does it mean? What does it mean? Every instruction is going to not take more than 2 bytes of locations. 1 byte, byte 0 and byte 1, which is a 16-bit value. Now within the 16-bit value, which is can be, if I write it in binary hexadecimal form, this is 1 byte and another byte. Okay, it could vary from this to this. Okay, it's large number of combinations are there, 2 power 16 combinations are there. Those many bits can be encoded into this 2 byte. Now each of those particular byte combination might correspond to a particular instruction that cortex m0 plus is designed for. So it is encoded in a different way. We are not going into the details of how this r0 value is encoded and how r1 is encoded and how move is encoded into the instruction. So it is going to be some 2 byte of value, the binary combination of that value. So that is going to be copied or stored in a binary form into this obj file. Suppose if you have an instruction like this, and not only this instruction, it has many more information like whether function call, label, jumping into something. So many things are encoded into the obj file, which we are not going into the details of it. But remember that what you need to answer in case if the question asks whether what is the input to a compiler and what is the output of the compiler, you should be able to answer saying that its input is either, if it is a C compiler, it is a C source code. If it is C++ compiler, it is going to be a C++ source code, and then the compiler is going to generate a obj file, which is a binary file having the information or having the content of all the assembly instructions generated by the compiler for a related to the instruction that you have used in the C compiler, C programming. Okay, so that's what is the answer for a compiler. Now, what is the next tool that we are going to look at? Assembler and linker and loader. Now, what is the assembler? Now, let us look at assembler. Assembler is again a tool which takes in assembly instructions. Okay, in our example, this is a dot s, capital S file. Whatever we have written in this course, many assembly instructions we have used. Those assembly files are going to be fed to this assembler. It's not going to be understood by the compiler. The assembler is capable of understanding the assembly instructions that you have written. Now, what is the difference between a compiler and this? The input what you are giving, and what is the output? Output is same as what obj gives because it is a binary representation of the assembly instruction. Only difference here is we are directly feeding the assembly instructions here which we have written, whereas in C compiler it is internally generating the assembly instruction by itself. The compiler is generating it based on your C source file, and then it is also generating the obj file, which is a binary representation of the instruction that it has generated. But assembler does the half of the job that compiler does. Okay, it is not expected to generate the assembly instruction because it is fed with assembly instruction. Its job is only to generate the binary representation of the assembly instruction, which is same as whatever I explained it in this case. So it's a one mark question, so I don't want you to write a long explanation about what I am giving you here. I want to give an overview of all the tools, but in the exam please manage the time accordingly and then write only what is an important point that you have understood from the video. Okay, that's it. So you need to know both are binary file representation of binary files which are representing the assembly instructions of a particular code for which the compiler or assembler is built for. Okay, that's it. Now what is a linker? Now linker is another tool which takes in all the obj files generated by the compiler or assembler. It could be a obj file from here, or it could be a binary file coming from the assembler, or it could be a library file also. Lib is also what is a reusable modules which have been written by the library developer, and it could be a printf function, or maybe you can also write a library functions, a string library. So they are also a binary representation of the core or a cortex m0 plus for which these libraries are built. Now linker's job is to link many of these binary files. It is not going to look into any of the text file or assembly file or a C source file. Linker is going to use only the binary files generated by some other tool. Okay, please remember that. And then it is going to build them all together, put them all together into a single another library. It could be another library, or it could be an executable which can be uploaded into a hardware. Okay, so now linker is doing that. Now what is the loader's job? Now loader, I said that the executable that is generated. So this is the executable. Remember, executable is also a binary file. It cannot be just understood by opening it in a text editor. Okay. Now this loader job is to suppose if you have a Raspberry Pi Pico board, okay, I'll call it as Raspberry Pi Pico, then you are uploading the code into this, right? So that loader's job is to understand the exe file or some other format, it could be any binary form, and then writing into the flash inside the chip, okay, inside the board. So there is a flash, and then there is a program running on the board, and you are using a USB COM port and then uploading it. So now the two loader's job is to take the executable and put it into the hardware. Okay, that may be a very high level explanation for this. Okay, I asked one question, okay, but I have explained to you many tools. Please understand all of them. Okay, I hope this is clear now. What is the significance of locality of reference in the software system, and how is it exploited by various processor architecture designs? Okay, now again, this is a loaded question. Let me give you an overview of this now. What is a locality of reference? Locality of reference means something is being referred. What is being referred is in a local area. Okay, that means they are all in the same location or nearby. Now, a processor, as I told you, a CPU is executing set of instructions. Now it wants to access an instruction, it is going to use a program counter, and it's going to put the address into code area, okay, or a text area, whereas assembly instructions in a binary form are loaded, which is in the memory. Okay, now it is accessing them. That means when I am saying it is accessing them, it is being addressed, and then the content of that is brought into the CPU, because if you want to execute a program, it needs to be brought into the CPU. And you know that it is a IR instruction register which is getting this instruction, which could be a 2-byte instruction, thumb instruction, or maybe some instructions are 4-byte wide. That means it is 32-bit wide instruction which are coming into the CPU, and then CPU is going to execute it. Now the locality of reference comes when the program is running in a processor. Now there are two things which are required for a CPU while it is running your program. One is the code which is coming in, which is a set of instruction, assembly instruction, may be generated by a compiler, or you are written your own assembly program. They come in, and then based on the instruction being executed, it is going to access some data. So data is also being accessed by the CPU, which is in response to the program which is being executed by the CPU. Now what happens is, for a program to run, as I told you, a C program will have code, some locations which are reserved for data, and some locations which are reserved for stack. Now, in a high level language, local variables and parameters are stored in the stack. And many instructions, push and pop, which are very specific as a processor, which is accessing using the R13 or a stack pointer register. Now, stack pointer or R13 is a 32-bit register which is inside the CPU, which is having the address of the stack. Now, what about the code? PC, program counter, which is also R15 in our case, having the address of the code area, which could be some different part of the memory. They all have different addresses, range of addresses. Maybe it is some 2000 to 3000. I'm just giving you a small number, and then this may be from 4000 to 5000, could be. Now, what about the data? Data, you know that there are instructions called LDR, SDR, store, and then LDM, STM. So those instructions use some specific register as per the instruction. Now that register will have the address which is pointing to the data area. So effectively, the CPU is using different registers to access different part of the memory based on the language as well as the processor. The different things will be residing in different area of the memory. So code will always be put in the code area, and the data which we are accessing, maybe arrays or whatever variables you are declared, global variable, they will be in the data area, and the stack will be all the local variables in the high level language. Whereas if you are writing assembly program, then you will be specifically writing push and pop, which will be stored in the stack area. So stack pointer, which is R13, is pointing at this location. Now coming back to the locality of reference, what does it mean? Any program, if it is accessing either stack or maybe a program or a data, it doesn't matter whether it is which part of the memory. what happens is it will access which are very local to a particular area in the code or data or a stack. Now, locality of reference means, now let me try to answer the question in particular. What is the significance of locality of reference in software system? So, the significance is what is being used recently, what has been used recently, either code or data, which will also be used in the future. Okay, recently used one will be used in the future. Now, that is one thing. In when I'm saying recent and then future, I'm referring to time. So, it is a temporal locality of reference. Temporal. Okay, temporal locality of reference. Now what about an array of data or a code which is inside a for loop? Okay, you have written a for loop and lot of code is there which is residing in a some part of the code area. Now when you are executing a for loop, you will be executing this quite often, right? So whatever instructions are there which will be again executed, so which are nearby, okay, all the instructions which are next to each other will be stored in the memory which are close to each other. So space wise also the code or a data or a stack will be used. So this is called, this is a temporal locality of reference. Okay, and in terms of code or data, it is a spatial locality of reference with respect to space, no, a particular area of memory. So you can talk about that. Now how does the software system exploit it? So how does the processor, how is it exploited by various processor architecture design? So for this, you need to talk about memory hierarchy. I am just telling you many things, but summarize it and write only what is required as per the question what is being asked. So how does that is exploited by the processor architecture? What you need to say is there is a memory hierarchy and cache. L1 cache will be very close to the CPU, and then L2 cache will be there, then maybe L3 also, then main memory. Okay, so what you need to understand is CPU when it is accessing any code or data, majority of the time it will find it in L1 cache, and then if it doesn't find it, then it goes to L2, otherwise L3. If it is not found anywhere, it goes to main memory. So what is being brought into the CPU is also copied into these locations before getting into the CPU. Okay, understand this, and then based on the question you write it, and then if it can be a short description, a small 2 lines of explanation or 3 lines will be enough. I don't want you to write all that have been covered in the video. It is only to give you an overview of what you have learned in this course, and you are supposed to know it before you move into the next course. So please understand everything what is being discussed in the video, and it will help you not only in this course but for the future courses as well. So effectively, how processor architecture exploits the locality of reference? Since the programs which are being executed are going to be accessing what is recently used in terms of temporal locality, as well as whichever area it has used, it will be using it very often. Okay, more often. So we are bringing the code which is being accessed more often in the lowest the memory which is very closest to CPU, so that it can be accessed only from this and takes less time for accessing L1 compared to accessing the main memory. Remember, main memory is farther from the CPU, whereas L1 cache, which is closer to the CPU, so it will access it faster with less time. So, and because of locality of reference, it will find it here only most of the time. That's the reason the processor architecture designs exploit the locality of reference. I hope this is clear to you. Now, what is NDNS? Explain it with the example. Now, this is to give you a summary of what is NDNS. Remember, a CPU is accessing the memory, and always the memory is laid out in terms of bytes. Remember, it's byte addressable memory. So always remember an address 100 is holding a byte value. That means B0 to B7 is stored. Okay, and then 101 will have the next byte value. So each address corresponds to one byte. Whenever I am saying that I am accessing a location, I am accessing a byte location and I am getting that byte value. Now, what does the CPU do? It is, in our case, we have a 32-bit registers. Always 32-bit registers are being used. Though I can access the memory only for a byte, most of the time I will be writing 4-byte value or 8-byte value or maybe more. Now, you know that a 4-byte value or in a register R0, suppose I have values which are 4 bytes wide. Now if I have to write it in hexadecimal form, maybe I will write it as AA. That means A is 1010 and another A is 1010. This is 1 byte value which is stored here. Okay, because 4 byte are there because B0 to B31 are there. So I may have a BB. I'm just giving you a random number. So BB is nothing but 11, right? So 1011 and 1011. So this value will be here in a binary form. And then it could be CC, which I'm sure you will know, 1100 1100 C. And then maybe I may have a DD. In that case, it will be 1101 and 1101. I will leave a space just to make sure that you don't get confused with so many ones or zeros which are together. Okay. So when I'm writing this value, I'm writing it as well as I'm reading it. Okay, let us assume that I am having this AABBCCDD and then I'm right to write into a memory location. Now let us again come back. I am interested in writing a value which is in R0 from B0 to B31 bits AA, BB, CC and DD. Now, as far as this 32-bit value is concerned, this is the LS bit and normally it's called LS byte also. This DD is LS byte and AA is MS byte. Okay, if I am writing it in capital, I can say that it is a byte. Now, let me say that and I have an instruction. Okay, I want to store it. So, STR and then I have a register R0. Okay, I want to store this value R0 which is here into some address R1. Okay, suppose this is the instruction that I am using. Now R1 is having a address which is pointing at some location. Okay, let me say that R1 is having address 1000. Okay, now this 1000 is actually a one particular location in the memory which is a byte. It can only accommodate 1 byte. Remember, an address which is given here can only address a location of a byte. But I am interested in storing a entire R0 value which is 4 byte wide. Remember, STR always stores a 4 byte value. Okay. And now how do I write it when I have only address of one particular byte location? So it is always taken that if I am storing 4 byte, I will store it in 4 consecutive locations. Now 1000, 1000, 2003, starting from 1000 to 1003. I have identified 4 locations in the memory where I want to store these 4 bytes. But I have a freedom now. I can decide to use or decide to store this value starting from this location, this byte, which is DD. I can store it DD first, then CC. I'll go from here to here, okay? And then I say BB and AA. But once I have decided that I am going to start from the LS bit or LS byte, it is called little endian. Okay, it's called endianness. Okay, endian, not Indian, endian. Little endian. That means I am starting from a little lower side because B0 has 2 power 0, right? It's a lower value compared to 2 power 31. Yeah, but bit in this location is 2 power 31, higher value. So I am starting with a lower byte, so it's called little endian. And how do I start? I start from the location 1000, whatever is I want to store. Now, when I am writing into memory in this order, I should also make sure that I read it also in the same order so that when I am reading from this location, DD will come and sit here, CC will come, BB here, and AA. So, what I wrote into the memory, I get back the same location, same values into the register. Internally in the register, they are all, again, this value will be here. No, it should come back to the same location. If otherwise, I will be doing it wrongly. Now, what is the other way of storing it? See, my idea is to store this 32-bit value into memory and then I should also get back that value. It is like this. When I am having suppose I am, I need to copy 4 pages of whatever assignment from someone, okay, or some notes from someone. 4 pages I have. I can write it in a, no, I have a notebook. I can write it, starting from the front page, okay. Starting from the front page, I start, this is the page 1, page 2, page 3, page 4. I am starting from the front of the book. End of the book is here. But somehow I want to maybe write it in the reverse order. Maybe I will start, what I will do, I will start writing from the last page of the book. and then I will say that the first page will go here, second page will go here, third page of my assignment will or notes from somebody else will go here. So I will do it like this. If I am doing it like this, I should also remember that I copied the notes in the reverse order, so I should start reading it from here, right? So I have a freedom to do it, and as long as I know in which order I am writing into it, I should also read it from the notebook in the same order. Similarly, what the processor does, it is having 4 byte values to be stored. It can decide to store it from this address in this way, or it can do it in the reverse way also. As long as it knows that I have stored it in this way, so when I am reading it back, I will read it in the same order. So I have the same value, which is AA, BB, CC, and DD. But I decide now this time that I don't want to store at 1000 this value. Okay, I will store AA first. Then I should also may remember that I should come from this direction. So BB, CC, and DD. That's it. So then this is I am starting from the higher byte, ms byte, and then storing it in this way. So this is called a big endian. So remember that this is how the endianness is used, and the processor can decide to do it in whatever way you want. So this is one good example of that. Okay, you what you need to do in the exam is just explain what is endianness and big endian, little endian, and give an example, and it should be done. Okay, I am writing it in this way so that you will be able to understand it better. Okay, maybe the exam will have a shorter question. Now, let me talk about what will be stored in the below str instruction. Maybe I will stop with question 5, and then we can start another YouTube video. Okay, so let me look at this question. What will be stored by the below str instruction into the memory if R1 has an address 2000? Now, this is how this NDNS I explained you, which is useful for you to exploit what I have learned or what you have learned. Not exploit, not the right word. Maybe use what you have learned in the previous explanation here. So before you look at the video, you can also try storing it, and then you will know what exactly you learned from the previous explanation. So how many bytes are loaded into the memory starting from the address 2000? So I just now I told you that STR stores 4 byte value, and it is storing the content of R0. I have given the content of R0 as 0x12 and 0. It's 0x means you can imagine it's not a 1, it's 000, 4 zeros, and 30 followed by 1 is 001. So let me write it in a binary form so that you will understand it better. So this value has to be stored in the location 2000. Now let us just look at it. As actually this is very good. So you will have str R0. Okay, I don't know. Did I mention R0 there or R1 there? Let me see. Very good. R0 only I have stored. And R0 is having a content which is 0x, 01, 02, 03, and 04. Now, what is the binary equivalent? I will write it now so that you will know what I mean by this 0x1, 2, 3, 4. And I said that R1 is having 2000. Now, it is very easy. You you know that always it will be increasing addresses in terms of byte. So 2001 address is here, 2002 is here, 2003 is here. Now each byte value will go, and you know that when I am writing in hexadecimal, each of those two values correspond to 1 byte. Please remember that. Okay, now what am I saying? What is it, a little Indian machine or a big Indian machine? You have to be very careful whether it what the Indian mode of operation is being mentioned in the question. It's a little Indian. So that means what? The LSB comes at the start. Okay. So I start storing it from starting from the LS byte. So 04 in binary form 04, I should write it as 0x. In binary form it will be 0000100. Remember that. Then 0x03 in binary form it is like this, because 1 byte corresponds to 8-bit values. So 0011. Now this will be 0x02. Then this corresponds to this 10 and 0x01. because I'm starting from ls byte, storing each byte into the memory, and the addresses are like this. If I have given 2000, now if I give something else, you need to be careful about it. Now what you need to do maybe is just to show the picture, which is, please come with all the tools which are required to draw some small picture, and then picture explains much more than words. So and it takes less time also for you to move on to next question. So please put a picture and then explain it in a two or three one or two lines. That should be sufficient. I hope this is clear to you. Now compare stm and push instructions with an example. So each, now what is, now let me again look at the question. um, STM and push. Okay. Now, why did I use these two instructions? Okay. STM is what? It's always, it's a memory related. Okay. CPU is sitting here and memory is here. Now, STM does store multiple. Okay. It's called store multiple. That means multiple bytes. Okay. Multiple register values, and then it is moving from CPU to memory. Now, what about the push instruction? Push also does pushing some register content into the memory. So both are the direction wise, it is moving from CPU to memory. Now let us look at the instruction as such. What you can do is you can just explain it with the instruction R0 and then R1 comma R2, because I have given multiple. Let me at least give one or two registers, but it doesn't matter. I can even have only one register also. And then push instruction, I don't give any other extra registers, but I will only say R1 comma R2. Suppose if I am doing like this, I can also change the order, but always it will be storing it in the lower number first to the higher number. And in terms of STM, I mentioned some other register also. Now, what does that mean? In push, I don't mention any register base address. Where do I know? How do I know? Where do I push this value? I am not giving any memory address at all. So memory address is implicit in push. And where is it supposed to take? It is supposed to take from R13. So memory address is indirectly considered to be from stack pointer. Whatever the stack pointer having is what is going to be used by the push instruction. Okay, which is called SP. Whereas in STM, you need to be specifically mentioning a register which is supposed to have the address. So that's one major difference between push and STM. Push assumes that it has to use stack pointer as the memory base. Okay. Now it has got the base address from any one of this register. Now it is supposed to store two values, R1 and R2 in both the cases. If you see both instruction, it is supposed to store R1 and R2 in both cases. It is supposed to push both R1 and R2. What I mean by that, whatever is in R1, where 32-bit value is moving into memory. It's copied into the memory. Please remember, when I am saying move, it is not going to make this value 0. It will remain the same, but it will be copied into the memory. Okay, the same content. How many bytes are moving? 4 bytes are moving. That means 4 bytes have to be copied into the memory. Now, let us look at both cases. I am having STM here and push here. Now push, I said that SP is pointing, so it is the address. Whereas in STM, R0 is pointing, that means R0 is having some address which is the location. So this is very clear. You can even draw a picture and show. Okay, that will be fine. Now only other difference is I am going to take 4 byte wide. Okay, you can mention this also in your picture, then it becomes easier to understand as well as for me to know that you have understood that in case of STM or in push instruction, 4 bytes are always taken. Okay, because you are mentioning the register content here, you are not saying that I want to copy only the lower byte or libel or whatever. You are saying entire registers to be saved. So you have to make sure that the memory that you draw is 4 byte wide, so that you don't have to go every byte wide, because if you go into the byte, then you have to worry about the NDNS, whether it's a big endian, little endian, all that will come. So right now we are not worried about that. We are just thinking that it is stored in some way, either following little endianness or a big endianness, doesn't matter. Okay, now R0 is having the address which is being pointed to. Now let me first talk about the push instruction. There is one more thing you should remember. It is a full descending stack. Okay, full descending. Descending means going down. Okay, whenever I am pushing, the stack is growing and it is going to go towards the lower address, descending. So this is a higher address and this is a lower address. Now what I mean by lower and higher address, suppose stack pointer is pointing at 2000, assume 2000 a binary form. No, sorry, decimal number. Now each location I said 4 byte. So another location, another address wherein another register can be stored will be 4 values lower than this 2000. So 996. That is one register will go because I said that 4 byte wide. All 4 bytes are sitting inside. Okay, like this byte byte. And then another location. Please remember that 992 because it is going down. So addresses are going to be decremented. So that is about descending part. Now what is full? The stack is following this convention. Okay, that means wherever the stack pointer is pointing, it's full. Now let me write it like this. That means it is full means something, some other content is already pushed into the stack and the stack is a pointer is pointing at it. That means what, if I am pushing some value, I should not overwrite that because it's already there. There's some values there, I don't know what was used earlier. Now I am interested in pushing R1 and R2. Now the convention is I have to store R1 and R2, two register values which are 8 bytes. That means I need a location like this, a 4 byte location, another 4 byte location. 196 to, starting from 196, 4 values, and 992 to 4 values. Now 2000 to 2003, already some values are stored. When I say 2000, that 1 byte is 2000, this is 2001, 2002, 2003. Then actually sorry, it is actually there in the top, don't worry about it. Now 196 means it is from this location I am storing a 4 byte value. So I have to go 4 bytes down because it is actually located, now 4 bytes are used from this address. Now when I am having 4 down and this one R1 I have to store, okay, push it, and then R2 also I have to store. Now I have a choice to make, either I can store it here or here, but the convention the processor follows is, anyway I need to use two addresses, both the locations of this one, and the next value I will be storing it is 4 bytes lower, 988 I will be storing. Okay, so it will be, you know going down 4 bytes, right, and then it will start loading it. So I need to store the lower numbered register which is R1 in a lower address. That means whatever address I have, I need to put R1, the lower register address here, register content here, 4 byte value, and R2's content here, because it's going to have 4 byte values which I am going to store. Now where does the stack pointer point at? Because it is supposed to point at the full location. So stack pointer will be updated automatically to point at this address. Okay, so when I am pushing next one, it will not push here because it's already full because R1 is having. If I use another push instruction after that, push R4, then R4 will come here and the stack pointer will be pointing here. So it keeps on going down when I am pushing something. Okay, so let me summarize it. What you need to do is push is from the address whatever is there, it will subtract 4 and then from that address it will be storing it. Okay, so it won't touch the value which is 2000 from this to this, and then it will leave out some space in 193. So you can imagine that these are all lower addresses which are being used, and then 192 is used, and it will not, it will use 988 only. Okay, I have forgotten this. So this value, so it will go down like this. Okay, so 4 4 each, it will go down. Now what about pop? When I am, suppose if I have to explain pop, you can assume that, suppose I have done one push. Okay, now imagine I have done one push, R1 R2. You might have got this is already pushed, and then now stack will be pointing at 192 1992, which is the address where R1 is point stored. Now if I do immediately pop R1 comma R2, now what am I doing? Stack pointer is pointing at 192. Immediately I am popping it out. That means it is the lower address. Now when I am popping it, based on the number of registers I am popping, that many number of 4 values should be incremented because it is going to go up now because I'm emptying the stack. So 4 into 2 value because 2 values I'm pushing. So 8 addresses it will go up. So 192 plus 8 I will do, and then it will start pointing at 2000 back again. Okay. Stack pointer will be updated to point at 2000 again because I am popping out the values I have loaded. But where do I get R1? So I have to copy from memory to register. I will copy from the lower address, which is 192, 4 bytes from there. I will copy into R1, and then another 4 bytes from there. I'll put it into R2 and make it point to 2000. Okay. So stack will be updated. So if I am saying pop and the current stack is pointing at, remember wherever the stack is pointing at, that address, that content, 4 byte content from that address will be loaded into the lowest number register. Okay, in the thing inside the pop instruction. I hope both push and pop are clear now. So I will stop here in the interest of time, and the video would have grown to more than half an hour. So see you in the next video. Bye.